This is part 2 of your section B electromagnetism tutorial, and here I just want to start off this graphic over here that we used in the last tutorial as well. We're just citing the source. It's from a blog called speedoflight299.blogspot.com. So if you want to see it, it's from there. Also, the book we're using is ICSE Physics, Concise Physics it's called. So just telling you that if you want to refer to what we're referring, those are the sources. And we'll be using an animation later, so we'll definitely be telling you the source for that as well. Before I move on to the working of a DC motor, I'm going to discuss the factors on which the Lorentz force, the magnitude of Lorentz force depends on. That means what should we increase if you want to increase the Lorentz force, or what should you decrease, so on. Now, the current flowing in the conductor, you denote current by I. If you increase this, then your force also increases. Now, if you increase the strength of the magnetic field, it's denoted by B. I don't think you would have come across it before. If you increase the strength of the magnetic field, F again will increase. And lastly, if you increase the length of the conductor, which means the length of the wire, if you increase it, again your force will increase. And these are all actually proportionality signs over here, which I haven't drawn over here. But from this you get F is proportional to IBL. And as you know, sorry, this should be a small L over here, even here. Okay, so as you know, if you have proportionality sign, you can introduce a constant and make it an equality sign. So we can write the constant as K, so IBL. And if you take the right SI units and everything, you can actually write this as F equal to IBL. I won't go into that, but just remember this formula. This is the formula. You won't get numericals, sorry again, it's a small L. You won't get numericals on the formula or anything, but you should know it. It might come as what does the magnitude of force depend on? Simple 2-3 mark question. Also, the magnetic field, you haven't come across this unit before, I don't think you have. So the unit for this is called Tesla, symbol is T. It's also called Weber per meter square, but what you should refer to it as is Newton per ampere meter. So that's Newton upon ampere into meter. So you could write it as just like n a to the power minus 1 and m to the power minus 1, small m, remember. So that's it for the factors. Now I'm going to move on to the DC motor and its working. So all you need to do in DC motor, I know it looks confusing when you first try and understand it, but you need to just look at it step by step. I think it's pretty good in the book, but that's as long as it's like a revision thing. I think the book teaches you assuming that you know a lot about it already. So we're going to put it in a simpler way over here. Firstly, I'm going to bring up the animation. Okay, here it is. So this is the animation. You can see the source is at the bottom. A person named, I don't know how to pronounce his first name, but Yves, I guess, Pelletier, and he's given his URL as well. So just look at the animation now. The DC motor, it has 4 stages. Now, one is when, I'm just going to pause it at the beginning so you guys can see. Okay, let's say this horizontal position is the first position. Now, it rotates 90 degrees. This is second position. It rotates another 90 degrees. That means 180 in total. This is third position. And and another 90, 270. This is your last position. And then, of course, it'll come back to your horizontal. But I've chosen this one because he's denoted I, he's noted all the magnetic lines of force as well in all of those 4 steps. So we're going to go over it pretty quickly. And I'm not going to go over the components and everything. The only important thing you need to know is that this red region, I hope you can see my cursor, the red region in this circular thing over here, which is connected to the circuit, the red is actually not connected to the circuit. So if you have the 2 reds on either side touching your wire, there's going to be no current, and you'll see that in a moment. So I'm going to keep this here, and you have your left hand rule right in front of you over here. So first position, I'm going to pause at the horizontal. Okay, here. Now this is how it looks. Let's call this 0 degrees. This is your initial position over here. Now you have to apply your left hand rule over here. Current is actually going this way. You can see the positive and negative marked. Current is going from positive to negative. It's not depicted here. Here. So positive to negative. He's shown the arrow here. Just follow the current here. It goes through, and let's forward this a bit. Okay, this is perfect here. So current is going like this. You can see the white arrows that depict the current. Now let's just take this top part over here, the yellow wire which is on the top. Apply your left hand rule over here. So okay, this is your conductor going like this. Your magnetic field lines are going like this. That's how it looks. Now just apply this left hand thumb rule here. So your index finger points towards magnetic field, so it's going down. Direction of current is rightwards. So you can see that your thumb will be pointing away from you, which means that if you look at his green arrow here depicting the force, that's also going that way inside the screen. So at this position, your Lorentz force is going to push that part of the conductor in the direction, the counterclockwise direction. It's going to rotate. And the opposite will happen when you look at the bottom part. And you don't need to apply the left hand rule. We already concluded that if you reverse the direction of the current, the force is also going to reverse. So you can see magnetic field lines are just the same. You're just reversing the current because the current goes like this in a loop. So at this position, this will be pushed, inwards towards you. So you can see that there'll be a it will be it'll be a counterclockwise motion over here. Now I'm going to pause it right now. Now over here you may notice that there's no arrow for I given here. There's no white arrows here. That's because if you can see the yellow, whatever this is, it's called a split ring commutator, but this yellow knob-like structure, it has those 2 red portions in the middle. If at this instant those 2 are touching the wires, the white wires on either side, over here and over here, then no current will be carried. Now let's just rewind a bit, and you see that this is rotating. It's rotating with a fair amount of force. Now, when it's rotating, and from case 1 of our earlier tutorial that when there's no current, the whole conductor will not move. There will be no force. So if you apply that, you should question that at that point, shouldn't it just stop moving? But that's not true. In theory, it should, but practically, you have inertia. Since it's rotating already, that inertia is going to carry it forward such that it rotates beyond that point. If you look at it again, it has inertia at this point. Now, in the next instant, it's going to touch the place where there's no current, but it's rotating so fast. It's not that fast actually, but it's enough speed so as to carry it around. So this will happen even right now. Whenever those 2 red parts come in contact, with the two white wires. So this is the basic working. You can go by step by step. If you look at first the horizontal bit over here, we know that it's going to rotate this way. Then you can look at 90 degrees. Again, apply your left hand rule. What you're going to see is that it's always going to, the top wire, this wire over here, is always going to get pushed inwards, while the bottom wire is always going to get pushed outwards. And also note, like, if we name this wire over here A and B, I should draw this here. It's something like this, right? Let's say that this is AB at this point here. The current is going like this. So now after this is AB, let's name this CD here. Now just notice that after one rotation here, this is where your CD will actually come on top. Your CD will come on top, and this will be AB. So at this point, AB gets pushed inwards, your CD will come out like this, and at this point, your CD will get pushed inwards, and your AB will come outwards. So this is the main principle behind it, and it all works on Lorentz force, and it has many practical applications. Everything around you, almost everything around you, which takes in electricity, will probably have a DC motor in it. Fans are run by, in fact, your computers also have coolers in them. Uh, Often you have computers with little fans in them. So it's a very practical thing. And again, there are certain ways of increasing the speed of how fast this rotates. The first is quite obvious. You increase the current. If you increase I, automatically the speed of the rotation will increase. Also, if you increase the number of coils, number of turns in the coil. Now here, just for simplicity, we're taking just one coil over here. If you look at the animation, it's just one coil. But you get these 3-volt toy motors in the market. If you actually open one of those up, you'll see thousands of, not literally thousands, but loads of coils. It'll be like this. It's just a huge mess over there. You can't see it very distinctly, but that increases the speed. Another thing is increasing the area of the coil. Say you have this over here, and you have this over here. That's a bit too messy, but you get the point that if the area covered by the coil is more, the speed will again increase. And the last is again related to what we've already done. You increase the strength of the magnetic field. So increase the strength of the magnetic field. Yes. Again, that increases the force, as we did in the first section. And that's it, really. The motor, it's an example of conversion of electrical energy to mechanical energy, rotational energy, actually, if you want to be a bit more specific, with mechanical energy. So that's it, and I don't blame you if you have a few doubts right now. If you do, you can watch the animation at the URL. Just search. In fact, this chapter, you can get everything on the net, because it's a common confusing topic. So you'll get many of these animations also for AC generator, and I'm pretty sure there'll be a few for section A as well, like electric bill and all, if you didn't get it. So that's always there. The URL is here. Um, Here it is. So you can visit this if you want to see the whole animation, the more animations there, I think. So that's it for DC motor. Of course, if you have questions, you can ask us or go to the net, as I said. That's it. And next time, we're going to be dealing with the AC generator.